Agentic reinforcement learning research requires constant modification. Researchers spend their time testing new advantage estimators, tweaking reward functions, and designing complex rollout schemes. But standard frameworks were built for ultra-large-scale parameter tuning. Every algorithmic edit threads through distributed backends, trainers, rollout glue, and plugin registries. The researcher inherits hyperscale complexity. What should be an afternoon's edit becomes a multi-layer debugging problem. We can see the cost of this complexity by looking at the footprint of traditional stacks. Systems like Virl or Megatron often require tens of thousands of lines of orchestration code, peaking at roughly 62,000 lines of code. Infrastructure built to deploy models at maximum scale prioritizes stability across distributed systems. But for research velocity, that architecture is a bottleneck. We need to separate the ability to scale models from the burden of complex middleware. Molt is a PyTorch-native training framework built to solve this exact problem. The goal is to keep the entire algorithmic flow compact enough that a researcher can trace it end-to-end without crossing an opaque abstraction layer. Molt directly composes standard, frontier-scale components. It snaps together VLLM for serving, Ray for asynchronous orchestration, and PyTorch FSDP2 for the policy actor. By relying on these native components, the complete reinforcement learning path operates on approximately 8,600 lines of code, a fraction of traditional stacks. By removing the middleware, a human researcher or an AI coding assistant can hold the entire system in their head. The framework achieves trillion-parameter scale while remaining completely readable. The boundary between the reinforcement learning algorithm and the execution environment is typically heavy with integration code. In Molt, the agent remains an ordinary Python program. Existing agents running against a stock OpenAI or Anthropic SDK can train exactly as they are. There are no specialized integration layers or environment domain-specific languages required. This code snippet shows how a chat agent simply routes standard SDK traffic using a base URL parameter. To make this work, Molt launches a loopback chat server in front of the VLLM engines. This server natively captures all the incoming SDK traffic as exact accumulations of tokens. Agentic Online RL has unusually quiet failure modes. The serving engine and actor evaluate nominally the same policy, but differences in tokenization or MOE routing can bias the gradient without raising an error. Molt enforces a strict token in, token out, or TITO invariant. Prompts enter the engine as exact, immutable token IDs, and completions return as token IDs, permanently bound to the log probabilities calculated exactly when they were generated. Because the text never passes through a tokenizer mid-episode, retokenization drift is completely eliminated. The result is a structural guarantee. The model never trains on a token it didn't generate. The data captured in the experiment is exactly the data used for the loss update. Moving to the orchestration layer, let's examine how Molt coordinates execution. Ray manages a single asynchronous queue that directly connects the agent pool, the VLLM rollout engines, and the policy actor. The system uses a streaming pool mechanism, constantly keeping prompt groups in flight and pushing experiences into the queue. Agentic workloads have heavy-tailed generation times, meaning some tasks take far longer than others. Molt uses a configurable queue depth to decouple the training throughput from this generation latency. When it is time for a wait update, Molt executes a partial rollout. It pauses the engems, broadcasts the updated actor shards, and resumes without discarding any of the in-flight generation requests. Because resumed requests might be mixing different policy versions, every single action token retains the exact log probability returned at the millisecond it was sampled. This ensures accurate importance correction when calculating the loss. This single asynchronous loop guarantees that the VLLM engines never drain their workloads, and the PyTorch actor never idles. Generation and training overlap continuously. Training mixture of experts models introduces a specific failure mode. Small numerical variances can cause the rollout router and the training router to independently select different experts for the exact same token. Molt solves this silent divergence using routing replay. The VLLM engine returns its exact per-token expert choices back to the trainer, and the FSDP2 actor replays those routes during its forward pass. Returning to our architecture diagram, let's see how Molt handles massive scale. It natively expresses complex parallel layouts via PyTorch FSDP2. Scaling up to a DeepSeek v3 class MOE model just requires changing the expert parallelism size using a single command line flag. Production-serving features like speculative decoding, prefix caching, and CUDA graphs arrive organically. Because Molt relies directly on VLLM, these features are activated as simple engine flags rather than requiring custom integration layers. Moving from a 4 billion parameter dense model to a 700 billion parameter MoE is a change of configuration, not a change of systemic design. The final step of the RL loop is returning the newly updated weights from the FSDP2 policy actor back to the VLLM serving engines. As the diagram shows, this weight refit happens via a direct NCCL broadcast. The weight synchronization bypasses the request router entirely. Each rollout engine securely loads only the specific parameter shards it owns. This keeps the request router dedicated exclusively to handling inference traffic without being bogged down. By eliminating a separate parameter server layer, this architecture maintains a direct feedback loop from agent action to policy loss and back. The primary engineering objection to a lean framework is performance. Does removing the multi-backend hyperscale architecture inherently destroy system throughput on massive workloads? To test this, researchers ran a matched protocol benchmark testing Molt against a state-of-the-art Megatron core stack, training a 30 billion parameter Quen model. This chart compares throughput on a controlled 16K context saying. The data shows the mean performance difference is within the range of cross-run variability. This lean PyTorch native loop delivers throughput comparable to the industry's heaviest stacks. And as trajectory lengths scale up toward 32K or 128K reasoning regimes, the optimizer step becomes entirely dominated by generation. That shrinks any back-end performance differences even further. A unified PyTorch native loop can match the performance of specialized production stacks while retaining the readability required for research. Because performance is matched, we can focus entirely on the researcher's daily experience. In Molt, advantage estimators are plain functions of rewards and groups. They are selected by name, completely avoiding complex inheritance hierarchies. This design keeps algorithmic edits highly localized. An AI coding assistant can trace the path from a command line flag directly to a tensor branch and straight to a metric output without getting lost in abstraction. When failures do occur, the lack of opaque middleware means the error is instantly visible, localizable, and readable. Massive infrastructural complexity is an inherited choice from an older era of static deployment. It is not an absolute mandate for frontier-scale AI training. Molt proves that extreme scalability can be seamlessly imported from hardened components like VLLM and FSDP2. This leaves the framework itself thin, readable, and optimized purely for research velocity.